Now, this unit circle that we just learned about is extremely important in trig. And right now I'm going to show you why, because I want to tie it into the 6 trig functions that we've studied so far and show you how what the unit circle has to do with the 6 trig functions. Now, you'll notice that I've drawn up here a unit circle. It has a radius of 1 unit. And then I've got a triangle that's, I didn't denote it here, but it's a right triangle, and it has a hypotenuse of 1. Now, notice that we defined, and I'll say this angle here is theta, and this angle here is theta. Remember, when we used right triangles to define the trig functions, we said this. We said that, for example, the sine of theta is the opposite over hypotenuse, right? So this is y over 1. Now notice, if we're dealing with a right triangle, that would just amount to sine equaling the opposite side, right? Since the hypotenuse is 1. Likewise, the cosine. The cosine is the adjacent over hypotenuse, which we don't have to put it over 1. It's just, x. We usually don't divide by 1. It's just understood. It's over 1. And tangent, what would tangent be? Opposite over adjacent, right? So that would be y over x. Now notice that what that means to us up here with the unit circle. When we're looking at the unit circle, and I'm not using one of our special angles here. I'm just saying some angle that we see in the circle, theta. And I'm saying in general, if we're looking at a unit circle, what is the meaning of the coordinates up here? We've got an x-coordinate and a y-coordinate. What's the meaning of those? Well, what we're going to find is that the x-coordinate is cosine theta, and the y-coordinate is sine theta. So that's one of the things that's very important. One of the important observations we make about the unit circle, because now we can take another look at the trig functions. And no longer, when we hear sine, do we think of opposite over hypotenuse necessarily. Now when we hear sine, we think of the y-coordinate of the unit circle. When we hear cosine, we think of the x-coordinate of the unit circle. On many occasions, that's the more convenient way to look at these trig functions. Now, of course, a lot of times we want to think of sine as opposite over hypotenuse, cosine adjacent over hypotenuse. Many times, it's best to think of it that way. However, being able to look at a unit circle and know that the y-coordinate is the sine and the x-coordinate is cosine is very useful, as we're going to see in many applications in our study of trig. Now, let's look here. If sine is y, what is cosecant? What would be cosecant? Remember the relationship between cosecant and sine.
It would be
1 over y. That's right. If sine is y, then cosecant is 1 over y. They're reciprocals, right? Now what about secant? Secant would be 1 over x, that's right. And what about cotangent?
It would just be x over y.
That's right, x over y. Now one of the fun things about trig is as you look at these definitions, you immediately start to see relationships that you may not have seen before, between the trig functions. Look at tangent. When we were talking about right angle trig, we often, we looked upon tangent as opposite over adjacent. Now all of a sudden we're looking at it as y over x, which is the same thing. Does that have any special meaning to you, to say that tangent is y over x? What's something else we could say about tangent? What is y equal to?
Sine of
That's right. sine theta, and what is cosine? X, that's right. So it looks like we've discovered that tangent is not just opposite over adjacent, it's sine over cosine. If you know the value for sine and you know the value for cosine, it's the ratio of those two. That's what tangent is. See? Now what about cotangent? What is cotangent? That's right. Cosine theta over sine of theta. Now these are two very important identities that we're going to look at down the line. But think about what identities we know already. We know the reciprocal identities, which you demonstrated that when you decided what cosecant was. We know the Pythagorean identity of sine squared theta plus cosine squared theta equals 1. We know that Pythagorean identity. And now we know these ratio identities, right? Do y'all see that? Okay. Any questions about this? So look at the significance here. Now we say this on the unit circle. If we want to know the value of sine, we look at the y-coordinate. If we want to know the value of cosine for a given angle, we look at the x-coordinate. So everybody understand that? And tangent, we look at the y over x. Okay. Now let's just look at some. Let's get some practice here. I've got a unit circle up here, and let's just say we want to find the sine of 2 pi over 3. The sine of 2 pi over 3. Well, here's what we do. On the unit circle, we find that angle. And it's over here. Here's 2 pi over 3. You see that? Now, we look at the y-coordinate. It's the square root of 3 over 2. So that's our answer. The square root of 3 over 2. That's our sine of 2 pi over 3. Does everybody see that? Now what about cosine of 2 pi over 3? Well, negative 1/2, that's right. You just look at the unit circle. See, with the unit circle, now you start to see, well, why do we need to know about the unit circle? Well, because look at all we can study the behavior of sine and cosine, for one thing, and the other trig functions, but what's going to be more immediate is when we start looking at, well, what is the graph, this function, this sine function, what does the graph of it look like? And we're going to look at that as well as the graph of cosine, and we're going to find this unit circle to be very helpful to us. Now, what about this? What about the tangent of 2 pi over 3? What would that be? What is tangent? Remember? It's the y over the x. So this is the square root of 3 over 2 over negative 1/2. So what is that going to be? Okay? Now, some of you, this was troubling to some of you. How do we simplify that? One of the easiest ways to simplify a complex fraction like that is just multiply the top and the bottom by the denominator. In this case, the denominator is 2, so I'll just multiply the bottom by 2 and the top by 2. And what that does is it divides out these extra denominators. So now look what we have. Up top, we just have the square root of 3. And on the bottom, we have negative 1. So this is just negative square root of 3. And that's your answer there. Okay? Everybody see that? Any questions about that? Okay. Now let's do this. Let's do the sine of 13 pi over 6. 13 pi over 6. Now, you might be wondering, well, that's not on the unit circle, so how am I supposed to do that? Look, this is 12 pi over 6, isn't it? Now remember last time we talked about, well, how do you graph these angles? How do you determine where 13 pi over 6 is? Well, look, divide 6 into 13. That quotient tells you how many half turns you go around the circle, right? So look, 6 will go into 13 twice. So look, you go 1 and 2. Now that would be 12 pi over 6, right? 2 pi. Well, what's the remainder? 1. So you go 1/6 of the way around, and that would be right there. Right? Ma'am? Right. You graph it. First thing you have to do is figure out where the angle is, because it's not really obvious because we don't have that point on the unit circle. However, when we go around here, we find it corresponds to this point. Okay? In other words, it's coterminal to pi over 6. It has the same terminal side. So now look, here's what we have now. It's going to be 1/2. See? And the cosine, likewise, is going to be square root of 3 over 2. And what about tangent? Okay. 1 over the square root of 3, that's right. And if you like to rationalize your denominators, that would be the square root of 3 over 3. Well, so your question is, what if you don't get exactly where it's, that's okay as long as you know what ordered pair it refers to. In other words, when you're determining where these angles are, you're not trying to be accurate and actually get the degree measure. You're just trying to understand what ordered pair it corresponds to. I mean, the sketch, this drawing of the angle, is just a tool that you use to get an idea about which ordered pair. You see that? Okay. Any questions about that? Now, let's notice something here. In this quadrant over here, this first quadrant, notice everything is positive. Because your x and your y, they're both in this first quadrant, they're both positive. I mean, we know when we move to the right and we move up, that corresponds to a positive x and a positive y, respectively. Now, what about if you're in quadrant 2? You notice when we evaluated an angle in quadrant 2, the sine was positive, being a y, up, and the x was negative because we're going to the left, right? So you see now, what we didn't worry about when we were just dealing with triangles was the sine. We were always dealing with positive lengths, so we never cared about what the sine of when I say sine, it's S-I-G-N. We never cared about the S-I-G-N of sine, S-I-N-E. It was always positive because we were always dealing with a length. That's not the case here. We see that over here in this second quadrant, cosine is always negative. Sine is always positive. In the third quadrant, sine and cosine are both negative. It's because of the way we plot points, right? If we go to the left, that corresponds to negative x's. If we go down, that corresponds to negative y's. Any questions about that? So let's just real quickly look at the sine situation here. Let me draw a circle. Or actually, let me just draw an xy axis. Okay, let's take a look at this. Now, remember that we say that if you're talking about the plane, the xy plane, we refer to this part over here as quadrant 1. And then we go around this way, where this would be quadrant 2, and then quadrant 3, and quadrant 4. And it's important that we know this because oftentimes you'll be asked questions and it's all dependent, part of the question will say this, theta is in quadrant 2 or theta is in quadrant 3. So you just need to know this. Now notice that quadrant 1, if you look at the ordered pairs, they're both positive in quadrant 1, right? In quadrant 2, you've got a negative x and a positive y. And in quadrant 3, what do you got? Negative and a negative. And that's right. In quadrant 4, you've got a positive and a negative. Does everybody see that? So look, in this quadrant over here, now, so you want to keep this in mind because oftentimes you're going to need to know the difference. Sine theta is going to equal 1/2. Other times it's going to equal negative 1/2, depending on which quadrant you're in. If you're in quadrant 1, sine theta might equal 1/2, whereas if you're in quadrant 3 or quadrant 4, it might equal negative 1/2. Okay? Any questions about that? No questions? Okay. Now let's move on to the next step. So it's best just to think of the xy coordinate system to remember, this is cosine, this is sine, and then tangent, of course, is the ratio. Remember, if sine is negative, cosecant is negative. Okay? If cosine is negative, then secant is negative. If tangent is negative, then cotangent is negative. Now, under what circumstances is tangent positive? Which quadrants would tangent be positive? The first, for sure. Everything's positive. Where else would it be positive? The third, right. Because if you divide a negative by a negative, you get a positive. So in quadrant 3, you have sine is negative and cosine is negative. So tangent is going to be positive. So is cotangent. And you can see where you have different signs, tangent and cotangent are going to be negative. So tangent and cotangent are going to be negative in quadrant 2 and quadrant 4. Everybody see that? Okay, now let's look at how we would put all this together to just work a simple problem. Let's suppose that you're given this. Let's suppose that let's suppose we have sine theta is equal to 2/3. Okay? And here's what we have further. We have this, that theta is between, let me say pi over 2 and pi. In other words, what we're saying is that that should be a theta. There we go. We're saying theta is between pi over 2 and pi. Now, what quadrant is that? It's between 90 degrees and 180 degrees. Which quadrant would that be? That's right. It's the second quadrant. So this is Q2. Now, what does that mean? In Q2, you know that you have a negative x and a positive y. Okay? That's immediately what you know. So let's suppose this is the setup for the problem. Now, we want to do this. Find the other 5 trig functions. Let's suppose that we're given this problem. Okay? Okay? Any questions? So we want to find the other 5 trig functions. Now, what do we know right away, actually? Before we go any further, what do we know?
It's going to be 3 over 2.
3 over 2. We know cosecant. We know what that is because it's the reciprocal. Now, we've got to find out what the other trig functions are. Now, let me just ask you this. What would be the sign of cosine? Positive or negative? Negative, right? So I'm just going to establish the signs first because we know it's in quadrant 2. Now, what about the cotangent? I mean the tangent, I'm sorry. What would be the sign? That's right, it's going to be negative. And I'll just put a let me give myself some more space. Does everybody see why it would be negative? Because the signs are different, right? Sine and cosine have different signs. And then, of course, we can find cotangent, and it's going to also be negative. Okay, and secant's going to be negative, or is it? Yeah, negative. Okay, so there's quite a few of these that are. There's 3 that are negative. Now, how would you go about figuring out? Well, what are the numbers then? What is the cosine of theta? How would you figure that out?
You can draw a triangle.
That's right. Draw a triangle. So here I go. Let's just get a triangle. Okay. Doesn't have to be. And we'll just call this theta. And actually, you know, it looks at. Okay, so we've got theta here. Here is the opposite over hypotenuse. What would this side up here be then? Would it be the square root of 5?
Yeah, sure.
Okay, square root of 5. Now, because using Pythagorean theorem, b squared equals c squared minus a squared. Okay, so here's what we do now. We just look at the ratios. The cosine is adjacent over hypotenuse. So this is the square root of 5 over 3. And there we're finished with that one. Now secant is 3 over the square root of 5. Right, it's negative in front. Now what about tangent?
It's going to be just a second.
Opposite over adjacent.
So it's going to be that the 2 over 3 over square root of 5 over 3. So we can just say
Okay, so
2 over square root.
so this is going to be the square root of 5
Right.
over 2, right? Because you flip the tangent. Okay. Any questions about that? So notice the steps.
Cancel out the 3s.
Sir?
Cancel out the 3s.
The 3 only came into play when we were talking about cosine, secant, and cosecant and sine. The hypotenuse was not involved in the tangent or the cotangent.
Okay.
Now, let's look at this. So here's what would happen. You would be given this information. And then you would be told to find the other 5 trig functions, and this is the process you can go through. Now, I don't attempt to draw the triangle in such a way that it reflects which quadrant it's in. If I had, this would have been a right side up triangle, and I would have had to flip it and all. The thing I do, I just draw the triangle and act as though, just to find the ratios. I use this bit of information here to determine which quadrant I'm in, and then I just establish the sign. I establish the sign, and then I go back and get the numbers. Any questions about that? How we do that? No questions?